Good day, everyone. Today, I will present the introduction part of our project, which cover our background, math framework, variable, and objective. Let's start with 1.1, background and challenge. Our target event is the annual grand dinner for a student society. The main problem is that normal planning uses guessing work to estimate food orders. This ignores what different guests want to eat, like chicken, meat, or vegetarian choice, which cause over budgeting and waste food. Our goal is to stop financial loss and food waste by using accurate data-driven planning. For 1.2 mathematical framework, our core tool is linear algebra, AX equals to B, and the advantage of this tool is that it changes real-world rules like club fund, guest count, or drink ratio, and also dessert percentage into clear math entries for perfect allocation. Now, let's move to 1.3 decision variable. We have 5 main items to find. For X1, we have nasi minyak ayam masak merah. X2, spaghetti carbonara. X3, ice cream. X4, fries. And X5 for iced lemon tea. For 1.4 project objective, we want to develop a strong matrix model that balances guest preference with fixed rules. Second, we want to find the exact food and drink numbers needed. Third, we aim to find the most cost-efficient setup using computer metric analysis. And lastly, we want to apply a clear system to stop over-ordering and completely eradicate food and financial waste. Now, let's talk about our problem statement, which have 3 main parts. First, the core challenge. Our main goal is to balance what our guests want to eat while staying inside a strict club budget for the dinner. We have 5 food variables to look at. The big issue here is that all food costs and supplies are linked together. If we just guess the number, it will lead directly to losing money, wasting food, or making our guests unhappy. Second, our logistical constraints, which are our strict event rules. As you can see, our budget limit is written as a clear equation, and we also have other rules based on our guest need, such as making sure the total food portion match our 85 guests, which give a simple equation like display in the slide. Then we also bring our mathematical question. Our team is limited because we only have 4 routes to find 5 different food numbers. This creates an underdetermined linear system where many answers can exist, and making a blind guess is so dangerous. So our target is to use linear algebra, which is AX equals to B, and computer metric analysis to solve this system, finding the most coefficient food and plan that perfectly satisfy all our guest and budget rules.
Now, let's dive into the core of our project, the methodology. To solve our catering optimization problem, we first define our system using 5 key variables represented as x1 through x5. These variables account for the quantities of different food items, desserts, and drinks required for our event. Our system is governed by 4 primary constraints, which is attendance, budget, drink ratio, and dessert limit. To find a solution, we arrange this structure equation into a standard linear model. Ax equal to b. As you can see in the metric formulation on the right, the coefficient represent the cost and quantity requirement for each item. We applied Gaussian elimination to convert this into reduced row echelon form RF. By analyzing the matrix, we found that the number of non-zero rows is 4, meaning the rank of matrix A is 4. Since we have 5 variables but only a rank of 4, the formula n minus r 5 minus 4 gives us 1 degree of freedom. This identifies x4, which represents price, as our free variable, denoted as t. This is a crucial finding because it means the quantity of rice can be adjusted, which then dictates the quantities of the other food item. To ensure absolute accuracy, we utilize several MATLAB functions. We use RF to confirm our row echelon form. We use rank to verify the metric rank of 4. The null A function allows us to identify our freedom path or the null space. And finally, auth gives us the basis for our column space. The MATLAB output successfully verified our manual calculation, confirming that x4 5 is indeed our free variable t. What does this mean in a practical sense? We observe that what we call a visual trajectory or a balancing act within the valid boundaries where t is between 0 and 85, we found a direct trade-off. If we choose to purchase more fries, increasing t, the system automatically shifts it drive up the portion of nasi minyak ayam masak merah X1 while simultaneously cutting down on spaghetti carbonara X2. This mathematical relationship ensures that despite changing the menu composition, our total spending remains perfectly steady at our 3,000 ringgit budget. In conclusion, this model provides the organizer with the flexibility to adjust specific menu item while mathematically guaranteeing that all logistical and budgetary constraints are met.
Next, result and analysis. For system analysis, the calculation confirmed that the rank of catering coefficient metric is exactly 4, given that the model track distinct variable. The system nullity is determined as nullity equal to n minus rank A equal to 5 minus 4 equal to 1. Following this mathematical framework, the model contains exactly one free variable, which is the row space as big a dimension of 4, mirroring the established rank of the matrix. Second, the column space similarly reach a dimension of 4. The third is this specific dimension for both the row and column spaces remain fully consistent with the matrix structural rank. The last one is the computational output from MATLAB strongly validate the theoretical attribute of an undetermined system where m less than n. For system dimension and rank nullity, first variable allocation n equal to 5, the variable trap food and beverage count across the banquet constraint. Next, the rank nullity theorem. Establish the fundamental balance of the linear system, which is rank A plus nullity A equal to n equal to 5. And operational nullity of 1. A single free variable, x4 fries, emerges as the control parameter t. This guarantees infinite solution within the budget. For system constraint, 4 independent operational constraints govern the logistic framework. First, attendance constraint. Second, budget allocation, RM3000. The third, beverage ratio requirement. And lastly, symmetrical dessert limit.
Moving forward, let's dive into the core algebraic structure of our catering system, starting with the row space and column space analysis. First, let's look at the row space. The row space is spanned by the non-zero rows of our reduced row echelon form or RREF matrix. Mathematically, it represents all the linear combination of our operational requirements. As you can see on the slide, our row space yields a dimension of exactly 4, which perfectly mirrors the structural rank of our coefficient matrix A. This tells us that out of our constraint, we have formed fundamentally independent equation dictating our system. And next, we evaluate the column space. Spanned by the original pivot columns, specifically columns 1, 2, 3, and 5 corresponding to the leading variables, the column space gives us the basis vector shown here. Just like the row space, the dimension of our column space is also equal to the rank, which is 4. This consistency confirms that our 5 menu items are structurally robust enough to map out a 4-dimensional target requirement vectors. Now that we know our system has a rank of 4, what happened to the remaining dimension? This brings us to the null space of our line of flexibility. While the previous space deals with fixed operational rules, the null space represents the homogeneous baseline where AX equals to 0. In real-world terms, it embraces all the potential decision pathways that allow us to maintain a strict constraint equilibrium. Because we have 5 decision variables but a rank of only 4, we mathematically end up with a nullity of 1. This dimension of 1 means we can perform parameter substitution by setting our free variables, which is x4 or the portion of rise, as the parameter t. We can solve for all the other food variables symmetrically. This creates a physical symmetrical trade-off. Every single increment in our side dish fries will dynamically and automatically balance out our main chicken meal portion against the spaghetti quantities. It provides that our catering plan isn't rigidly stuck. It has a mathematically calculated fluid line of flexibility. Then, to tie everything we've discussed together, let's look at the ultimate structural relationship between the subspaces. We can break this down into two beautiful mathematical principles. First, the rank nullity equilibrium. Our system's dimension perfectly satisfy the fundamental rank nullity theorem, where rank A plus nullity A equals to n, which is 5 total decision variables. This 4 plus 1 equals to 5 balance that show that our 5 independent operational constraints strictly lock down 4 dimensions of our project, leaving exactly 1 degree of freedom, our parametric trajectory t for flexible price allocation. Second, let's talk about their geometry. Orthogonal complementary in 5-dimensional domain of R5. Our row space and null space exist in a state of orthogonal complementary, meaning row space of A equals the orthogonal complement of null space of A. They share a zero intersection, meeting only at the trivial zero factor. Why does this matter to our event committee? It provides independent scaling. It means any change we make within the null space to shift our menu flexibility will never violate or break the deterministic row space, which hold our fixed budget and attendance rules. We can safely adjust our food combination along this path, knowing our RM 3,000 budget and guest satisfaction remain perfectly safe.
Let's move on to the discussion of our geometric visualization from section 6.1 of the report. Even though our system mathematically lives in a 5-dimensional coordinate space, our nullity of 1 collapses the entire infinite solution space into a single 1-dimensional straight line. However, because we cannot order a negativity amount of food or drinks, our real world scenario
introduce non-negativity constraint. This splits the infinite line into a strictly bound feasible region, mapping exactly over the parameter range 0 less than and equal t less than and equal 85. Any value chosen outside this segment would violate our constraint, either causing the budget to overload or forcing food quantities to drop below zero. When looking at our 2D projection, the trajectories reveal clear clear linear trade-off. Nasi minyak ayam masak merah costs up, while spaghetti carbonara and ice cream slope downward to preserve our budget equilibrium. Meanwhile, the drink variable x equal to 5x as a stationary constant function perfectly parallel to the parameter exists, meaning it's still locked at 85 portion no matter what. To translate these geometric trajectories into practical decisions for our commit, we evaluate the absolute limits of our feasible line segment. In scenario 1, if we choose the minimum boundary where t equal to 0, we order 0 fries, but the system forces us to buy 53 portions of spaghetti carbonara. This poses a heavy risk of food waste if most students prefer local rice. In scenario 2, if we choose the maximum boundary where t equal to 85, we serve fries to all 85 guests, but our dessert drops to absolute zero. Completely leaving out ice cream is a terrible operational choice for a formal grand dinner. To avoid this bad extreme, our commit pick a balanced middle ground by setting our parameter t to 42. This mathematical sweet spot gives us a highly realistic menu like 46 portion of nasi minyak ayam masak merah, 39 portion of spaghetti carbonara, 43 for ice cream, and 42 portion for fries and our constant 85 drinks. This satisfies generous student preference perfectly while spending exactly 3,000 ringgit. To wrap things up, our project has successfully shown how linear algebra can solve real-world event planning challenge. By building a structured matrix model, we successfully balance different food preferences with a rigid budget. Utilizing MATLAB computation and identifying fundamental metric space completely remove random guessing and trial and error from our process. We prove that understanding our one-dimensional null space gives our commit a safe, data-driven track to adjust food portion without breaking the club budget rules. Ultimately, this algebraic approach guarantees 100% budget compliance and zero financial waste, giving our student association a perfect operational template for all future format events. That is all from us. Thank you very much.